All right, y'all, we're going to add to the notebook again, and we're going to talk about something today that is so exciting to me. So on 89 and 90, we're going to introduce a brand new mathematical operation. So think back to when you first learned about a square root. Square root was really interesting because we could figure out what number times itself was the number inside the root. So like square root of 25 is 5. And that felt really weird and strange at first, but then the more we practice it, the better we get at it. So I have another mathematical operation to introduce to you today, and it is called a logarithm. So we're going to call this logarithms intro. We'll go to 89 and 90. So on 89, I have this little thing flipped in half. I have a lovely book. I also have on page 90 this half book here. Okay, so let's start there. First of all, what the heck even is a logarithm? And what does it look like? So if I had something that looked like, or the way that we write a logarithm is like we have log, and then we have a little base number. So instead of like an exponent number, it's like a little mini bottom number. So like log base 2 of 32 equals 5. And this is a true statement. Log base 2 of 32 does equal 5. And that's because what a logarithm is asking is this base number, so 2, to what power is 32? So a logarithm is asking this number to what power is 32? So like logarithm is just shortcut to say to what power, like to what power is. I don't want to have to keep saying that over and over and over again. To what power is, to what power is, to what power is. So they just went with logarithm on that. Don't know why. Could have picked something cuter. It's fine. Logarithm sounds scary. It's not. So we're just doing 2 to what power is 32. And I'm pretty sure 2 to the 5th power is 32. And so sometimes it can be really helpful to rewrite a logarithm in exponential form. Just because we want to understand how exponents and logarithms are related, because they are actually inverses of each other. They undo one another. They are opposites of each other. An exponent will give me a really big number, while a logarithm takes really big numbers and makes them small. So kind of like the opposite of like square rooting and like to the 2nd power, except these powers are changing. So the powers get even bigger and bigger and bigger. So these are even bigger numbers. So taking like this one here, I could rewrite that in exponential form, but that's not super interesting. So let's try a new one. If I had something like 3 to the 4th power, I know that that is 81, because 3 times 3 times 3 times 3. And what a logarithm will do for me is if I didn't know that power, like if I didn't know it was 4, a logarithm will get that power for me. So we would say log base 3 of 81. So 3 to what power is 81? Well, we know it's 4. And so the super nice thing, again, we want to be able to say a logarithm correctly as well. So this is something else I want to add to here. The way that I say this, because we want to speak math well, is I would say log base 2 of 32 is 5. So that's really nice that we say it that way, because when I'm talking about an exponent, the big number is the base. And then this base number, this basement number, this bottom number is also your base. And then a logarithm will always equal an exponent, and this is my exponent. And then this is kind of the result, I suppose. I'm just not going to label it. These two are always easy for me to figure out, the base and the exponent. And like where they go is super important. And then there's only one number left, so it's just got to go in the other place. So let's try this out and open some up. 2 things that we want to be successful at for today is really knowing how to evaluate a logarithm and then knowing how to rewrite logarithms and exponents. So When we're evaluating, we're asking how much. So this is asking that key question. To what power is 64? Instead of saying all that though, I'm just going to say log base 4 of 64. And I think that's 3. Or log base 4 of 16 is 2. Because 4 to the second power is 16. Or log base 5 of 125 is 3. Because 5 to the third power is 125. Here's where it can get a little interesting. So all of these had small bases and big numbers. This is opposite. And so if I have log base 343 of 7, we're thinking 343 to what power is 7? If I have a big number getting smaller, that's like taking a root. And I think we want to take a cube root here. The cube root of 343 is 7. Same idea on this one because we have a big base. So log base 64 of 4 is 1/3. Because 64 to the 1/3 power will like cube root me and make me 4. Okay, now we're back to small bases, big numbers. So log base 6 of 216. 6 to what power is 216? I believe that's 3. Because 36 times 3? That feels wrong. I'm just going to double check on my calculator. 36 times 6. Oh, LOL. Got it. Log base 3 of 1/243. So this is interesting because we went from a small number to an even smaller number. But I kind of think of it almost as a small number going to a big number under 1. And like exponents that make me go under are negative. So I know that this is definitely negative. And then I think it's 5. Like 3 to the 5th power is 243. And then negative flips me. So I think if we're fractional, we want a negative involved. Log base 2 of 4 is 2. Because 2 to the second power is 4. Log base 2 of 16 is 4. Because 2 to the 4th power is 16. And then we're back to our fractional logarithm. So log base 6 of 1/216. That 216 we had before, and it was 3. But now we're under. And so the way to get under is to be negative. So negative 3. Okay, so now all of these over here want me to convert. And you can just sort of think about it like I was talking about on the front of this. So I'm going to do like one of each. We're just sort of thinking about it. Like this is an exponent right now. So I need to rewrite it as a logarithm. And the way that I correctly say a logarithm is I do log base. And the base here is 1/5. A logarithm always spits out an exponent. And so then the y has to go here. So that's kind of if I'm just thinking about it. Same thing if I have to go the other way. So if I have a logarithm already, we're going to rewrite it as an exponent. So when I say log base u, I know that my base is u. A logarithm always spits out an exponent, and then it equals this other number, 15/16. Now we're not solving anything here. We're just rewriting. And so another way to think about rewriting is I have a little loopy trick. So let's take a break from this. We'll come back in just a minute. Let's go over to this one here that's folded in half. I want to talk about our little loopy trick. So if I have a logarithm and I'm trying to convert to an exponential or vice versa, so log to exponent or exponent to log, you always want to start your loop at your base, and then we loop around until we get to the last number, and we write the numbers in the order that we passed them. So I started here, I passed this, and then I ended here. So I start with B, I go to X, I end with A. The same thing happens with an exponent. So I start at my base and I loop around. I started here, I passed by here, and I ended there. Now I need to add a logarithm. So log base B of A is X. Okay, so we're going to come back to this one in a second. Let's keep rewriting. So if I wanted to use the loopy trick instead, I would start at the base and loop around. So log base 9 of x is y. Or again, when I think about it, base number equals an exponent other number. Same idea here, except for now we're going the other way. Oops, wanted to end at x, just kidding. So we already had the logarithm. This is going to be an exponent. We're going to be 7/4 to the y power equals x. And again, we're not solving anything, just rewriting. So here I'd have log base 6 of x is y, because the logarithm always spits out an exponent. Here we're going to go exponential, so we start with our base. Log always spits out an exponent equals the other number. Or if we use our loopy trick, we start at the base and loop around. So we're going to be log base b of 1, 2, 3 equals a. If we use our loopy trick here, we're going to be an exponent because we started logarithm. So v to the 4th power equals u. Or if we're just thinking about it, here we're going to be a logarithm. We have base u always spits out the exponent, and so v's got to go here. Here we're going to rewrite it as an exponential, so we got log base 2, so 2 is my base, always spits out an exponent, equals v. Or if we try our loopy, boop. So log base 8, a was next, b was last. Here we do our loopy. We are already a logarithm, so no logarithm this time. We're going to be y to the negative 8 equals x. Okay, so we're just rewriting, so we know how to go back and forth between the forms, because seeing it as an exponent is sometimes helpful. Now, you sometimes may encounter, coming back here, a logarithm with no base. So if you see something like log of x equals y, so there's no base, there's a missing base. A missing base is always a base of 10. Okay, so if you don't see it, then your base is 10. So some quick examples here. If I had log of 100 and we wanted to evaluate, we're thinking mystery base. So 10 to what power is 100? I think that's 2. Or like log of 10. So 10 to what power is 10? I think that's 1. Or this. Log of 1. So 10 to what power is 1? Any number to the 0 power is 1. If I had something like log of 0.1, which normally I'm not a fan of decimals, but this is interesting to think about because that decimal to me is actually not a decimal. I just make it 1/10 in my brain because it's in the tens position. So we're really 1 over 10. So 10 to what power is 1 over 10? It just flipped, so -1. And maybe we notice a little bit of a pattern here. And maybe a little bit of a pattern here. And so if I had log of 0.01, now we're in the hundredths position, so we're 1 over 100. I think that'd be a -2. Okay, so kind of if we have no base, my base is always 10, so we don't want to be tricked up by that. Another weird thing with logarithms that we want to put on the front here. If you recall, the last time we talked about a very important new number, the number e. The number e is lovely. It's a lot like pi. It is a beautiful number. It has a lot to do with exponents because that is kind of the asymptote that our exponential growth was approaching when we kept compounding more and more and more times. And so because e is so closely related with exponents, and exponents are logarithms opposites, E is also very closely related to logarithms. It's so special that it actually gets its own logarithm. So when your log base is E, the number, we instead use a special logarithm called the natural logarithm. Oh my gosh, spelling. And what a natural logarithm is, and this is kind of weird, is they use the letters ln for natural logarithm. I mean, I guess NL, but like, why not just do NL? I guess to make it look sort of like a logarithm, but like a little different. So it's still got the L at the beginning. I don't know. So silly. So if we saw the natural log of E, it will also not put a base because the only time we use natural logarithm is if our base is E. So this is really asking me E to what power is E? And I think that's 1. Or if I had the natural logarithm of 1, so E to what power is 1? Well, any number to the 0 power is 1. Or this is really interesting too. If I saw natural log of E to the 3rd power, so E to what power is E to the 3rd? Let's just think about rewriting this. So this would be rewritten as E to what power is E to the 3rd? I mean, wouldn't it just have to be 3? It's just 3, right? So weird. If we rewrite this, totally. So E is special. It gets a special logarithm. Let's try a couple more. I know this is getting a little long, so jumping into our magical book. We have that exponents can be rewritten as logarithms. The common log is when our base is 10, and we don't see it. So again, if I had log of 100, we know that's 2, because my common log is 10, base. The natural logarithm is base E. So we only use ln when my base is E. So if we had ln of E, that's 1. Okay, so just a few little weird things to add to the already weird thing. First of all, we got some rewriting. So if you already feel good about this, this is a good time to skip, or you can try and come back and see how we do. But here, because we are already a logarithm, we want to rewrite as an exponential. So we can do the loop. 2 to the 5th power is 32. And guys, they should always make sense. 2 to the 5th power does equal 32. So that's good. Or here, if I think about saying it, log base 7, and then always spits out an exponent is 1. And this is correct, like 7 to the 0 power, anything to the 0 power is 1. Here I have no base, so that means my base is 10 to the negative 2nd power is 1 over 100, which again, that makes sense because negative slip me, and then 10 to the 2nd is 100, so 100 on the bottom. And then lastly, we have a natural logarithm, which you usually see it like this. I feel like sometimes people confuse this with like 1n, but it's ln. So natural log has a base of E. So we're doing E to the negative 1st power is 1 over E. And again, that makes sense because negative slip me. So I'd have E on the bottom to the 1st power to do. Okay. Or we can take an exponential and rewrite it as a logarithm. So we need log, and then we put our base. Always spits out the exponent, and then 1 over 36. Always spit out an exponent. And I think that makes sense because we went from a big number to a fractional number. And so we should be negative. Fractions, negatives flip me. Okay. Log base is 81. Always spits out the exponent, 1/4. to the third. And think about that. If the base is big and your number is smaller, then we're fractional. We like took a root. So that makes sense. Another way to think about this one, if we do the loopy trick, we'd have log base 10. Although we can be a little lazy because if my base is 10, then I don't need to put it. Of 100 is 2. You can put the 10, but you don't have to. We can be lazy if we want. And then lastly, because my base is e, we're going to use a natural logarithm. You don't have to put the e down here. Again, we can be a little lazy. It's understood that natural logarithm's base is e. Always spits out the exponent, and so then e goes here. Cute. Let's try a couple more. Evaluate. So we're trying to figure out how much. So log base 7 of 343 is just asking the question, 7 to what power is 343? I think that's 3. Ooh, my logarithm has no base. So that means the base is 10. And this is in the thousandths position. It's like 1 over 1,000. Which, because it's a fraction, I know I'm negative because negatives slip me. And then 1,000 I think is 3 tens. 10, 10, 10. Okay. Looking at C, we have log base 1/3 of 729. So because there is a fractional move here, negatives always flip me. So it's definitely negative. And so like the negative will flip the 3 and now flip the 1/3, so now it's 3. Then I'm thinking 3 to what power is 729? Oh my gosh, that's got to be big. So 4 is 81. 5 would be probably not enough yet. Is it 6? OMG, calculator. So 81 is 4 times another 3 is 243 times another 3. That's got to be it. So that's 6. Oh. Yeesh. Getting a little weirder. Log base 16 of 8. So 16 to what power is 8? Kind of none. But if I can like square root 16 and then it's 4, but I can't get 4 to 8. I could also fourth root. Ooh, yeah. Okay, if I fourth root 16, now it's 2. And then 2 to the third is 8. So I rooted it and then I had to raise it. These can get tricky. Looking at E, we got log base 27 of 1/9. So I see a fraction action probably is going to be negative to flip. And so if I flip it, then we're like thinking 27 to what power is 9? And again, we got smaller, so I know I got a root. I can't square root 27. I could cube root it. Let's try that. So if I cube root it, we're 3. Oh, and then I square it, so it's 9. There you go. And then negative flips me. Oof. Lots to think about. Ooh, okay, here we had a special logarithm, so natural logarithm. So my base is e, and we're thinking e to what power is 1 over e to the 3. Now, I actually kind of like e's because usually they're just going to show you their power, and the power is 3, but it's on the bottom, so negative. Super nice. Ooh, this base has no base, so that means the base is 10. So log base 10 of 10 to the 12th means 10 to what power is 10 to the 12th? 12. Okay. Log base 8 of 128 is asking me 8 to what power is 128? Like 8 times 8 is 64, and then times another 8 I think is getting, I don't think we're getting there. So 64 times 8 is 512, which is too big. So I think I have to root it. And I can't square root 8, I can only cube root 8. So now it's 2. And then 2 to what power is 128? So I can probably get there. I know that 2 to the 5th is 32. So we're out of 5. Like I got to keep track. We're out of 5 for 32. And then we times by 2 and we're 64. So now I have 6. Oh, and then if I times by 2 again, I think we're there. Yeah. So 7. OMG. So we took the root And then we raised it 7 times. Craziness. Ooh, okay. This is interesting because normally when we have fraction action, we're negative, but both of these are fractions. So we actually don't need a negative this time. I really just can ignore the fact that it's a fraction almost and be thinking 5 to what power is 3,125. Even though they're both under, it doesn't matter because they stayed consistent. It's only when we go from a non-fraction to a fraction that we need a negative. So I feel like it's got to just be 5 to some power because 3125 ends in 5. I just don't know how many 5s I need. So I know 3 5s is 125. And then another 5 gets me 625. And then probably just one more. Yeah, so 5 5s. So 5. OMG. And then last but not least, this is interesting because it seems a little bit intimidating. We have this equation here that is asking me to graph, and we don't know how to graph yet, and that's actually okay. We don't need to know how to graph yet. We will later. We want to circle the points that will be on this graph. So they're giving me an x and a y. I can just plug them in for x and y right here and see what happens. So we'll have 5 equals -3 times log base 2 of -4 plus 6 minus 2. And then we just want to follow good order of operations to evaluate. We have to do what's inside parentheses first. So this is a question now, like, is it equal? -3 times log base 2 of 2 minus 2. Now this minus 2 is not part of the parentheses. So my next step is really to do the logarithm. The logarithm is like an exponent, and I've done what's in parentheses. So I have to evaluate my logarithm next. And log base 2 of 2 is asking 2 to what power is 2? So that's 1. And now we're back in easy land. So I just have -3 times 1, which is -3 minus 2 is -5, which is not +5. So this is not on the graph because they do not equal out. However, if we try the next one, so we'll put y -10 in, and then we have -3 times log base 2 of 2 plus 6 minus 2. Oh my goodness, I write too big. So it's a question. We're going to do what's in parentheses first. We'll have log base 2 of 8. Then we have to do our logarithm. So log base 2 of 8 is 2 to what power is 8, and that's 3. And it's being smushed up against this -3. And so we get -9 minus 2, which is unfortunately not 10. Goodness gracious, it must be this last one. And I have no room for it. Let's try our best here. So we're going to have -14. Does that equal -3 times log base 2 of 10 plus 6 minus 2? Okay, so parentheses first, we'll have -3 times log base 2 of 16 minus 2. Now we got to do the logarithm. So log base 2 of 16 is 2 to what power is 16, and that's 4. And now we're in easy land. So -12 minus 2 is -14. So this one is on the graph. Yay. Oh my gosh, that was so much, guys. And we're going to practice logarithms so much more. So good luck.